And these are all just descriptors to help you figure out if you have something in your house, can you figure out if it's an acid, a base, or a neutral compound? And so I think the most helpful of that is the thing tasting sour or tasting bitter. That might sound crazy to you because typically if you're in a chemistry lab, I do not want you to go around tasting the chemicals. That's not the way it works. But these are instead in here in case you have something like maybe these gummy worms that you see here below. Those taste sour. So whenever you taste something that is sour, know that that's an acidic compound that you're eating. Whereas if something tastes bitter, that's going to be a more basic compound. And then you're looking over here at the soap. Anything that feels slippery is going to be more basic. And so those are your soaps, that kind of thing. And so if you feel it and you feel like it's slimy or slippery on your hand, it's because it's reacting with your skin oils and that's producing the hydroxide. The hydroxide is producing the slippery substances that you feel with the soap. And then also something, just an extra interesting tidbit to you. Acids are really important in chemistry. In fact, it's the number one chemical that is produced in the United States is in fact sulfuric acid, which is an acid. And so these are really important compounds. They're used so much in every single part of our day. And so it's good just to know how are they classified. If you go look in your cabinets or in your cleaning supplies, which are acids, which are bases, etc. These test strips, they're used all the time for hot tubs, pools, that kind of thing. So knowing that all it is some dye that's pH sensitive, and that dye changes colors when exposed to an acid or a base, and that is how you're able to figure out what the pH is. It's kind of important to know, but for the most part, this is chemistry that lots of people that have never used chemistry before can figure out.
There are three main classifications of acids. We have Arrhenius, Bronsted-Lowry, and Lewis. Each one is just a different way of looking at whether or not something is an acid or a base. So to begin with, we've got these examples here shown of strong acids, and we'll talk about what strong acids versus weak acids means momentarily. But if you take any of these, hydrochloric, hydrobromic, iodic, nitric, perchloric, or sulfuric, all of these will break apart in solution because they are ionically bound. When they break apart, the proton, the H plus, is one product, and then the other one is their conjugate base. And so that just means everything that remains besides the proton. And so those are all acids based on the Bronsted-Lowry and the Arrhenius definition. All of these Arrhenius and Bronsted-Lowry acids are also Lewis acids. Notice how the inner circle is contained within the outer circle. And so Lewis acids are any acids that accept an electron pair. And so with these are all going to be classified the same way as Lewis acids, but they're also Arrhenius and Bronsted-Lowry. And we'll talk about more what that means later. All right, so here's another example of acetic acid, where acetic acid, you can't really tell really easily, but you guys all know that acetate is a polyatomic ion, and so if you take acetate plus a proton, you're going to get acetic acid. But you can see that that proton is one of the things that would come apart whenever you throw it into water. Another example is sodium hydroxide. You might think, oh, that has a hydrogen, clearly it's an acid, but you would not be correct because sodium hydroxide, it's sodium and then the OH, the oxygen and the hydrogen, are covalently bound together. So when you throw them into water, they break apart, but as sodium and hydroxide, not as sodium and a proton. Therefore, sodium hydroxide is not an acid.
So whenever you're looking for these, this is literally what's happening. You have like hydrochloric acid reacting with water. Hydrochloric is your acid it's your donor, so therefore it's the acid, whereas water might have accepted that proton, therefore it is the base. So in this situation, water is the base because it's accepting the proton. Hydrochloric is an acid because it's donating the hydrogen. All right, so question then. How do we know that these are or aren't acids? Because I already gave you those first couple caveats. What's literally happening? So in this case, you got your hydrogen at the beginning, and it is attached to sulfate. And so this is a polyatomic ion attached to a hydrogen. And so when this falls apart, it's going to break apart the two ionic parts. So the hydrogen ion and the sulfate, they're going to break apart from each other, thus releasing hydrogen in the solution. So this would be an acid. Same thing goes for here. You got hydrogen attached to a polyatomic, that of nitrate, and then when you throw it into water, they're going to break apart. And so I'm going to know that these are acids because I've looked at polyatomics prior to this, and if you recall back, I think that was Unit 1, just kind of remember those polyatomic ions. So if you see them and you see a hydrogen at the front, they're going to break apart well. But if you have things like this, NH3, hydrogen's not at the front, hydrogen's at the end. Hydrogen is also not in carboxylic acid. Therefore, you're like, what is this? Well, something to note. You need there to be an ionic bond in order for the hydrogen ion to pop off. So before you had a H with a polyatomic. Polyatomic is a charged particle. That of negative, the protons are positive. In this case, your nitrogen is a nonmetal, your hydrogen is a nonmetal. Two nonmetals bound together means it's a covalent bond. Whenever you have a covalent bond, it by definition is not an acid ever. Same thing here, carbon, nonmetal, hydrogen, nonmetal. Therefore, covalent bond, not acidic. And so that's what you're looking for. Proton at the front, proton at the end if it's a carboxylic acid. If it's in a covalent bond, it is not an acidic proton. It cannot pop off. So when we're looking at something such as sodium hydroxide, you have sodium bound to a hydroxide molecule. When you throw it into water, you release sodium ions, which are the same sodiums from sodium chloride, which is your table salt, and hydroxide. And so hydroxide is that basic element. So Arrhenius said anything that donates a hydroxide is going to be a base. Bronsted-Lowry wanted to go a little bit further and said, all right, I take you, Arrhenius. I'm going to encompass you. I'm going to say, yes, everything that's a hydroxide is a base. But you can still be basic without having hydroxides. And so he went on and performed a whole bunch of really cool experiments to prove this notion. And so in doing so, let's look at table 7.2. You'll notice everything pretty much has a hydroxide. Anytime you see that OH group, just check it off and be like, base, that was easy. But then you have something like ammonia. Ammonia down here is a little annoying little compound, right? So it doesn't have a hydroxide. You can't tell just by looking at it really quickly that, oh, I know for a fact that that is a base. Instead, you have to do a reaction in order to tell. So let's try and react it with a proton. Because we knew from the prior slide that with NH3, you can't strip off one of those hydrogens because nitrogen is a nonmetal, hydrogen's a nonmetal. So we know we can't strip a hydrogen, so it's not an acid. So let's throw an acid to it and see what we produce. And it will, in fact, accept it. So since it will accept a proton, we're going to classify it as a base. But how can it then also be classified as Arrhenius? It doesn't work that way. Everything that is Arrhenius, so if you're in the center of the circle, you are also considered a Bronsted-Lowry base. But things that are not Arrhenius, but only Bronsted-Lowry, they are things such as ammonia that could produce hydroxide if reacted with water. And that's what you see in this reaction here. So ammonia, is it Arrhenius? Does it have hydroxide built into its chemical structure? No. Therefore, it's not an Arrhenius base. Can it accept protons and form a basic compound? Absolutely. And so that's why it is considered a base, because protons, it will react with water, thus forming hydroxides in solution, thus making it the solution more basic. So kind of to recap that, Arrhenius or anything that you look at the chemical formula and you notice, hey, it's got a hydroxide. Bronsted-Lowry are those that will react with protons to produce something that is basic. And so that of ammonia is a great example.
I haven't really talked much about Lewis acids or bases up until this point. And the reason I haven't done that is because you really need to have a strong understanding of Lewis structures before you can discuss Lewis acids and bases. And so a Lewis structure just has these dots and these lines that show you how elements are connected in space. And it's really important to use this type of system for covalent compounds. So in this case, we have the nitrogen shown here with two dots next to it. That's supposed to be an electron pair. And so what happens is it has a free electron pair that it can donate to a boron, who can now accept the electron pair and form a new complex. So in this situation, the ammonia is serving as our Lewis base, the boron trifluoride is accepting the electron pair, and it's acting as our Lewis acid. And so together they form this nice pretty complex over here. This will make more sense when we get into Lewis structures, so don't worry too much about this definition at this time.
All right, so this is another just pictorial reaction of ammonia reacting with water. And you'll notice that in this case, water is your proton donor, making it the acid, whereas ammonia is your proton acceptor, therefore classifying it as the base. All right, so amphoteric, that's a fun definition in your textbook. It is any substance that can behave as an acid or a base. And I hope you noticed in the previous slides that if water reacts with hydrochloric acid, it's going to accept that proton from hydrogen, from hydrochloric acid. When it does that, it becomes H3O+, which means it was the proton acceptor, and therefore it was a base. But if you react it with ammonia, it's going to take that acid and donate it to the ammonia, making it be ammonium. Therefore, in this situation, it's a proton donor. Therefore, it's the acid. So sometimes water likes to be an acid, sometimes it likes to be a base, so it gets a fancy word called amphoteric. Or another way of saying that is if water reacts with itself, it can act both as an acid and a base, and it can self-ionize, thus producing that H3O+ and the hydroxide. And so these are just two little definitions that are tossed in here as well, just kind of help you remind you that sometimes you've got your acids and your bases, and they can play both parts of the field. All right, now, neutralization reactions. A neutralization reaction is what occurs when an acid reacts with a base, producing a salt and water. And so these salts are the same salts that we've looked at before, where a salt is a ionically bound compound. You've got a metal plus a nonmetal. So in the situations down here, you've got hydrochloric acid reacting with sodium hydroxide to produce sodium chloride and water. Sodium is a metal, chlorine is a nonmetal. You've got a metal plus a nonmetal, therefore it's classified as a salt, an ionic bond. And the second equation, you got potassium, metal, chlorine, nonmetal, reacting, ionic bond, it's a salt. Okay, and so that's just the reaction is what is always called, if it's a neutralization reaction, you always have acid plus base is a salt plus a water. And so here's just a couple more examples for you where you've got the salt being produced by the reaction between an acid and a base. So let's say we throw a molecule of hydrochloric acid into water. Hydrochloric is a strong acid, which means the hydrogen and the chlorine will completely break apart like what you see on the left. And so notice all of these purple versus all of these red. These reds are supposed to be your hydrogens, and the purple is supposed to be your chlorines, okay? Or whatever other compound is attached to your strong. But if you notice, when you throw it into solution, they're no longer attached. They're broken apart. And that's what it means to be strong. It has nothing to do with concentration. Okay, it also has nothing to do with being burned. You can be burned just as easily from a strong acid as you can from a weak acid. Okay, all it has to do with was when you throw it into water, what's being produced. The strong acids are considered strong electrolytes. So when you drink your Gatorade, you're replenishing your electrolytes. All that means is there are a whole bunch of charged molecules inside of your drink. Strong acids do that. They produce a whole bunch of charged molecules. And so they carry a charge. They're completely dissociated. Whereas if you take a weak acid, so acetic acid is one example. If you throw acetic acid into solution, the hydrogens are supposed to pop off. But instead, not every hydrogen pops off. And so I've circled all the ones that are in the bound state. Throw acetic acid into solution, throw some other weak acid into solution, they're not all going to pop off like the weak acids do. Some of them stay together in a bound state. And so when you're looking at this is important because weak acids act completely different than strong acids. And it's all because of this, of weak acids, they don't dissociate fully. If you can just remember that definition, you'll be fine. So how do you tell the difference between a strong acid and a weak acid? Well, what I do is I memorize a chart like this. All right, this is one example. There's lots and lots of charts that list, here is the example of strong acids, strong bases. But for our class, if it's on this list, it's strong. If it's not on this list, we're going to consider it weak. Okay, so I listed some common weak acids down there: acetic acid, hydrofluoric acid, hydrocyanic acid. I also listed some weak bases. And so when you're looking at this chart and you're trying to decide, is it strong or is it weak? If it's on this chart, it's strong. If it's not, it's weak.